reference frames, entanglement in quantum field theory and quantum causal structures, working under the supervision of Professor Bruckner, after which she moved to the University of Queensland as a postdoc researcher, where he worked on methods for discovery and control of causal structures in quantum systems, with applications to quantum technology and to the joint foundations of quantum theory and gravity. So welcome, Professor Costa. And the title of his talk today is Quantum Causal Structures. Professor Costa.
Hello.
Hello, yeah. Welcome, Professor Costa.
Yeah, so if I can share the screen, how do I share the screen?
Yeah.
I think I need
so there's a button. Yes, you see a green button which says on the top, share content. There's a green tab on the top panel, share content. It says share content with an arrow, upper arrow.
Upper arrow, sorry, I am on Zoom.
Do you see the top panel? So there's there's the audio, then there's a video, then there is a share content.
So
there's a box with an arrow.
So I have a share screen, but it says host disabled participant share screen sharing. So I think I need some host permission.
Yeah, sorry,
can you change the,
you can do.
Yeah, can you try it again?
Yeah. Okay, can you see the screen?
Not yet. Yes, now. Yes, we can see it. Dr. Costa? Yes, yeah. Please make it full screen.
Yep.
Yeah, thank you. Start.
Okay, so can I start? Yep.
Yes, please start. Yes.
Okay. Yeah. Thank everybody for being here, and thank you for inviting me to this online session, Kolkata and the world. So please, if you can send me some notification. So I have 45 minutes, right? Maybe I'll. Okay. Try to stick to that.
Around 45 minutes, and then 15 minutes of questions.
Yeah. Okay, so I thought to start by saying a couple of words about me, but I've been given a very nice introduction, so I will not have to say much. Maybe since we are meeting remotely, I will just share a picture so I can see a bit bigger picture of myself. I'd like to say I'm the one in the middle, but unfortunately I'm not. I'm the one with the beard. So that's me, my son, and my partner. And so I will go very briefly because this was already mentioned. My life history has taken me around a few places. I was born in Milan, in Italy, in the last century, where I did my undergraduate studies. I lived for a while in Vienna when I got my PhD. And then I was for quite a few years in Brisbane, in Australia. And very recently, I moved to Stockholm. I'm currently not in Stockholm. I'm back in Brisbane for some travel accidents. No, not accident, but for current traveling. So what do I want to talk about today? Quantum causal structures. I want to give a bit of an overview about the field I've been working on for the last several years. And this is a field that in fact arrives is the combination of many different motivations. So I will give you just my perspective, how I got interested in this. And that is, one can think very generally, how do we describe things in physics? And you can get a sort of very common picture. For example, if you're talking about quantum physics, you may want to say, what are events? Events are some observable things that we can see. We can think of events happening in space-time. And how we describe these events, typically what we need to do is to assign some quantum state in the past of all the events we want to describe, and then we evolve the state, and then we make measurements, and then we evolve the measurements. And then if we have some light structure, there could be some causal influence. For example, event A here can influence event C and not event B. And you can start to abstract this type of reasoning, and you can very easily see that you can abstract everything into some kind of circuit model where you have some initial state, and a set of quantum systems that evolve, and you can describe your events through, for example, measurements and the evolution through some gate. So the common thing in all this way of thinking is that all the events have a definite causal order. So you can always say, and a definite causal structure. You can always definitely say A cannot influence B and A can influence C. And if A can influence C, then C can definitely not influence A. So this is a very standard and basic way of which we do, I will say, almost all of physics. But there are a few reasons why one might think this is not the full picture. One of these reasons come from combining quantum theory and gravity. So you will know that in general relativity, the presence of matter, of mass, distorts space-time, not only space, but really space-time, which means that in principle, if you have matter that is in superposition, this can create a quantum space-time. And if you start to try to put events on this quantum space-time, you so realize that you might end up in situations where you cannot really say if an event is before another or after another, because the light construction might be in a quantum superposition. So this is one of the motivations. And we have an article that characterizes a bit more in detail this scenario. Another motivation is that, in fact, if you start to think about these quantum causal structures, you soon realize that these can potentially work as quantum resources. And one can think, well, okay, it's maybe a very unfeasible type of resource, but then it turns out you can perform experiments that very closely simulate or reproduce those indefinite causal relations without any need of quantum gravity. And I will, if I have time, I will briefly explain at least one setup where you can perform this type of experiments. There are other situations where one may want to consider events without a fixed causal order, even in classical distributed computations. So for example, if you think about the internet or about any situation where you have a computation that happens at different nodes, and these nodes send the signals to each other, then it's actually a very well-known and very pressing problem to determine or understand the causal relation of events. Because if you start to have delays or some uncertainty in the way the signals are transmitted, you might not know a priori which events are earlier and which are later. So this is an independent motivation for thinking of scenarios without a causal order pre-assigned in advance. So these are all motivations, but how do we even start to do physics without having a background causal structure? Since this is the way we usually think about physics, we formulate most of our theories. And so what we have to try to think is that we want to describe these events in some space-time, but without really space-time. So we want to have a description that starts with these events without having a reference to background space-time. And so instead of a quantum circuit that connects these events, we need some more general type of object that connects these events. Now, one thing that one way one might get stuck in trying to understand this type of scenarios is what I would call the evolving state fallacy, which is something that, in fact, I will briefly discuss. That is also a problem in the characterization of more concrete things like non-Markovian open systems. So what is evolving states fallacy? That's the attempt to describe everything in terms of an evolving state. So, and that again, it's something very common. You think that you have a system that you describe and it's evolving in time. And then the way you should describe it, this system, is by assigning a state at each time. So if you have a quantum system, that will be a density operator. And so you say there should be a density operator at time 1, time 2, time n, and then maybe you try to find some evolution equation. Now, to give some sense of why this is not a good idea, try to understand, to think about this scenario. So this is the weather prediction for tomorrow in Kolkata. I didn't take the prediction for today because it was 100% rain at some point. So I tried to find something a bit more interesting. Now, you see that here they give you a percentage of chance of rain at each hour or at each interval of time. So this is, if you think of this as an evolution of some state, the state here is something like the probability to get rain. And now I can ask you, what is the total probability to get any rain in Wednesday? Can you deduce it from this time evolving probability? And well, if we were in person, maybe I will try to get a raise of hands. Maybe you can think for a second how we will try to compute these probabilities, but maybe I will just give you the answer. The problem is you can't. So the reason is that what you're given here is a sequence of marginal probabilities. So you're given the probability for rain at time 1, time 2, time 3. But what you need is the union of the probabilities at all these events at time 1, time 2, time 3. So the object that you should be considered is not this sequence of probability distribution, but a joint probability distribution across times. And the problem is, you know, there is a 39 probability that it rains between 2 and 3 p.m., but you don't know if this is independent of the previous times or the later times. You don't know if suddenly there can be rain and it's independent of the weather before or after, or maybe there is a big cloud and it's almost certain will come over, but you don't know at what time it's coming. So the crucial thing is if you have this time evolving picture, you will be missing some correlations across different times. So what you should really think about is that each event is some independent variable or some independent source of some independent random variable, and you should consider joint distributions even if they're distributed in time. So this leads us to try to formulate all advanced quantum theory. So instead of trying to think of a time evolving state, which will have as a classical limit this marginal probability distribution, we need something that is the quantum version of what we call a classical stochastic process, which is a joint probability distribution across all times. And so that's what I will try to present, what I will present today. How do we construct such a framework? And so the starting point is to understand how do we describe events. So we say that we have to focus on the description, to start from a description of events without a background causal structure. And here we should clarify that when we talk about events, there are different ways one can understand or define or think of events. And in physics, we mostly have two meanings of this word. One meaning is that is often employed in general relativity, or at least in some formulations, is that an event is a location in space-time. So, for example, a set of coordinates. So some geometric location. A different point of view is that an event is something that happens. So, for example, a measurement outcome. You perform a measurement on a system. This gives you an outcome, and that's your event. And this second way is the one that we can use as a starting point of our general construction, because if we can start from the quantum description of events, and to do that, we don't need a reference to our background space-time. So when we talk about an event, it's not a location in space-time, but it's something that happens like a measurement outcome of a measurement. Okay, so this is our task. We need to characterize what are quantum events. And so when you go to kindergarten, you might be told that so quantum events is something that something observable. For example, a particle has a certain position or things of this type. So the result of an observation. Many introduction one is told that observables are described by self-adjoint operators in quantum mechanics. That's not a very modern or very general view. The kind of elementary school version of quantum measurements is POVM measurements, positive operator value measures that I assume most of you will be familiar with. So this is a set of operators, E with the subscript A, and A is your measurement outcome. So it's telling you that for what are the possible outcomes of your measurement. So you have a quantum system coming in, you perform some measurement, and then you have a possible outcome. Now, this description is actually not sufficient for what we need to do, because this only describes the probabilities to get some outcome when you perform a measurement, but doesn't describe how your system is transformed. But now we want to describe events that potentially are time-like separated and can influence each other. So we need a description of event that also takes into account how the system is transformed upon measurement. So here comes our high school version of definition of a quantum event, which is quantum operation. So that's the most general way quantum mechanics describes an event. And in a bit abstract terms, this means that you have to consider an operation that maps some input space to an output space. So these spaces are spaces of density operators. So these are quantum operation is something that should map a state into a state, any state to any state, and these are known as completely positive maps. This is the bit more formal definitions, but if you're not too familiar, just think that this is the most general transformation that you can associate with any operation or any transformation of a state. As a concrete example, you can think of a projective measurement. So if you perform a measurement that tells you, I found my state, my system in the state psi, then the operation corresponds to projecting your initial state to the state psi. And so in general, these operations include non-deterministic operations with a possible measurement outcome. As a particular case of operation that is useful to construct the theory is deterministic operations. So you can think of these as scenarios where you make a measurement, but you forget about the outcome, or you don't consider, you discard the outcome, or even just transformation, deterministic transformation on the system that you may want to describe. And so these are, as before, completely positive map, but with additional condition that they're trace preserving. And the reason is that states have to be normalized with trace equal 1. That is what telling you that probabilities are normalized. And so a deterministic operation is one that preserves the trace in the state. As a particular example is, for example, a unitary transformation. Your state comes in and then you rotate it according to some unitary operation. In this case, there is no measurement procedure associated, but it's still one example of a quantum operation. And more generally, if you put everything together, you get what is called an instrument. An instrument formally is a set of CP maps, so a set of a non-deterministic transformation that sums up to a deterministic transformation. So this label A represents the measurement outcome, and the fact that all the maps sum to a deterministic one is simply representing the fact that you are considering all possible outcomes of your measurement. Okay, so this is our description of events in textbook quantum mechanics, and this is our starting point for our construction of quantum mechanics without a background causal structure. So what do we need to do? Is what should we try to get in our construction? We should try to get, as we were saying, the joint probabilities for events. And the point is that these joint probabilities, we want to get them through a formula that doesn't care what is the doesn't care about the causal relation. So something that in pictorially represents this blob around these boxes without telling what is the order or the connection between these boxes in advance. Now, a couple of technical slides here. If you make some assumption, which can be summarized in assuming that locally you cannot distinguish your model from quantum theory, so all your operations are consistent with getting a quantum system in, measuring and sending it out, then you find that this probability can be written as multilinear functions of your CP maps. So each event at each location, which we can imagine as a local laboratory, will be associated with some CP map, and the joint probability will be given by a multilinear function. And you can derive this axiomatically from some requirements that represent local quantum theory. And this function is something we call the process, and is in a way a generalization of what we call a state, because it's what gives you the probability for a set of events. Now, this is a little bit abstract, but it becomes a bit easier when we introduce something called the isomorphism. So this is something that maps, that connects maps to states. So if you have a map that goes from, that is defined as a function from an input to an output state, space, this can be represented equivalently as a state that lives in the tensor product of input and output. So you can think of, instead of describing a transformation from input to output, you are describing something like a two-time state that is defined across the tensor product of input and output. And here is the technical definition. Again, I will not enter too much in details. But so this is just to say that this is defined as a joint operator as if it was a density matrix with subsystem input and a subsystem corresponding to the output. And if you describe maps in this way, then you get a very familiar look of this general probability rule, which is simply a trace rule formula. Different sources define it with different notation, conventions, transposition. But the main thing is that you have your joint probability will be given by the trace of the tensor product of all your CP maps times an object, a matrix that we call the process matrix, which is defined in the tensor product of all input and output spaces. Just to mention that formulas of this type have been derived over the year over and over. So it's a very powerful tool that people have discovered in many different contexts. Now, this is very similar to, now the question is, what is this process matrix W? So this is now the central object of our study, that what characterizes quantum causal structures. A way to link to what we know, the formalism we know about from quantum theory, is that now these measurement operators MA and B represent what in the usual formalism are observables, with the only difference that now these describe can also describe transformation, but formally they just work like observables, and this process matrix formally just looks like a state. In the sense that if you have an observable and a state, your probability rule has exactly the same form. The new thing is that now, even if we think of it as a state, this is a state that does not that it can allow arbitrary causal relations between these events. So in the usual formula, you will have instead of W, you will have a state, and instead of MA and B, you will have say P of M elements. And then in that case, there cannot be any signaling between these different events. So if you discard the outcome of say measurement A, then there is no change in the probability distribution for B. But now in this case, there can be causal influence. So W can encode, because it can encode arbitrary correlations between these measurement outcomes, it can also encode the signaling correlation. So it can also encode the causal relations. And all the causal relations are somehow incorporated into this process matrix. Which is, it works like a state, but with some constraint that ensure normalization of probabilities. So to get a little hang of it, we can go through a couple of examples. So we focus on bipartite processes. So we have an event A and event B. And now we can think of what are all the general causally ordered scenarios, so the usual known ones. How does this process look for known scenarios? So the simplest scenario is where A and B are two measurements on a bipartite state. And in this case, the process looks like a joint state across the two input spaces and identity over the output spaces. So if you plug this W into this formula, then you will get probabilities that are exactly the same as the usual Born rule given a state rho. Different scenarios where A is before B, so there is signaling from A to B, but not from B to A. In this case, the process matrix is a tensor product of a state that goes into Alice lab, into the lab A. And then you have an operator T that is the Choi representation of the channel from A to B. And so you start to see here some structure that you have encoded in the process are all the correlations. So the channel T that goes from AO to BI, it's what correlates, for example, a state preparation that Alice can do and the measurement that Bob can do. And Alice's measurements will detect the initial state rho. So that's a second known case. That's how a channel from A to B looks like in this formalism. A bit more generally, we can have channels with memory, which is the situation where the system that goes into Alice's lab is correlated with an external environment that does not go into the lab, but that can interact with the output prepared by Alice. And after this interaction, it goes into Bob. So this is what is called a channel with memory. And again, if you plug this W into the general rule, you will exactly get the probabilities from causally ordered scenarios. So So this is actually some interesting general cases channeled with memory that is worth thinking about, because already in this case, even if the events are causally ordered, this is already one of those scenarios where this time evolving state picture doesn't really work. So already in this case, we can see that the quantum version of what of this classical stochastic process is this process matrix, and it's easy to see that if you just try to build the state, say that here you try to build the state that goes into Alex's lab, and then you try to build the state that goes into Bob's lab, and you only give this information, this will not be sufficient to recover all the correlations between Alice and Bob. So, so this gives the answer that is useful for the study of non-Markovian systems, and gives you the quantum version, the quantum analog of a classical stochastic process defined as a joint distribution of variables across time. And this is something called, can be called a quantum combo. It has different names. We call it a causally ordered process. Yeah, and as you said, it can involve an arbitrary interaction between the system and environment. Something to note here in this description, again, I want to stress that this W can be considered as a state over time, which is something that you don't do usually in quantum theory, emphasizing this concept that if you typically, when you consider time evolving systems, you give a state at different times, but you don't give a joint state across times. You can give a joint state across different systems that can be separated in space, but if you have events separated in time, usually you don't give a joint state. But here, when you have this process matrix, it can be seen as a state over time. So these input and output spaces can be seen as a temporal subsystem. So a subsystem at time A and a subsystem at time B. Formally, these are represented exactly like subsystems in quantum theory, in the sense that you build a joint space using the tensor product. Now, this is everything about causally ordered processes. But now we want to know, okay, is this the most general thing we can think of? And some generalization that becomes quite natural in this formalism is a situation where the causal order is not known. So concretely, you can think of a scenario where you toss a coin, and with some probability, you put event A before B, or with some other probability, you put event B before A. So this is a scenario that doesn't have a natural description in quantum theory, because in a usual formulation, you need to set the causal order of events in advance. However, in this formalism, it has a very simple formulation, because you simply take the convex mixture of a process that has A before B and another process B before A. And these are processes that we call causally separable. So this is similar to the notion of separability as opposed to entanglement. So something that where I can imagine that there is an underlying causal order, but you just don't know which one it is. And of course, one of the questions of interest is this the most general scenario? And it turns out it's not the most general scenario. There are things that are called indefinite causal order. So something like a situation where I cannot even imagine a classical hidden variable that determines the order. Now, there is a mathematical example that can be written in this way. These are Pauli matrices. Alice and Bob are both getting a qubit. So it can be formally proven that it's not separable, but this is not very enlightening, because it's not very clear how it relates to any. So this is just a mathematical expression, and there is no clear implementation or a realization as a physical process. However, there are, so this was the first one that we found in one of our first papers. However, there are some other scenarios that are a bit more intuitive. And to understand one such scenario in connection with the original motivation, which is causal relations in general relativity, you can think of a scenario where you have events that are defined by the ticking of a clock. So you define, you have two quantum systems, and you define event A as an operation that is performed, say, at the second tick of clock A, and event B is defined as the second tick of clock B. And you set up your situation such that if nothing else is around, these two are at the same time, so they're space-like separated. So there is no causal influence between them. But now if you start to bring some massive system nearby, then you have that gravity induces time dilation. So now the second tick of event B ends up being in the future of event A. So crucially, from the point of view of B, his event is exactly at the same time, regardless where is the mass. It's just the relative order with the event of A now changed. But of course, if you now bring the mass closer to A, then it's event A will be in the future of event B. So the causal relation depends on the position of the mass, and now we can think of making the mass quantum. So it can be in two quantum states, state right or state left. And then I will not go through all the details here, but just to say, if you prepare the mass in superposition, then you end up with something like a causal superposition of orders A and B. To be more precise, this is not really a superposition, but it's more entanglement between the position of the mass and the causal relation between the event. In the sense, and you can't really define this superposition without having this extra control system. Or maybe a better way to think of it, this is quantum control of causal order depending on a control system. Here maybe I will go a little quickly through these details because it's perhaps a bit more formal, but just to say that this scenario has a relatively simple representation in terms of process matrices. You can actually, in this case, you can write your process matrix as a rank 1 projector. So you can interpret the state as a pure state. And the pure state is an equal superposition of two vectors that correspond to the two different scenarios. So the first is the scenario with the mass on the right. So the cat R represents the mass being on the right. And then you have a vector that represents the process AP4B. And then you have the other element represent the other branch of the superposition. And so here again, you can see clearly that this is something that represents entanglement between a control system, which is the mass, and a vector that represents the causal relation between A and B. Okay, so people call this superposition of causal order, but I'm actually not very fond of this term because it's not a pure superposition. You need this control. And now to briefly mention, so this was in this gravitational scenario, which is if you start to put together the numbers, what type of masses you need, you will need really big masses and to keep them in superposition for a very long time. So nothing that is even remotely feasible with modern technology. But it turns out that you don't need giant masses to create indefinite causal order. And so here is another scenario that is a bit more concrete. So here you have a picture of a scheme of an interferometer. So imagine that from the left, you have a photon arriving, and then these PBS are polarizing the splitter. What they do is that if the photon is horizontally polarized, each PBS will let the photon through. If the photon is vertically polarized, then each PBS will act as a mirror and the photon will bounce. And in the middle, these U0 and U1, these are unitary operations that are performed on some other degree of freedom, other internal degree of freedom of the photon. So not polarization, but it can be frequency, for example, or it can be spatial mode, so the shape of the beam, or anything like that. So we can see what happens if we start to prepare a photon in the horizontal polarization. So we have the control system can be in two states, 0, 1, which is, for example, vertical, horizontal, and the target is any finite dimensional system that is prepared in some pure state psi. So we start with the photon vertically polarized and see how it goes through. So it goes through, it goes to U0, then goes through again, goes to U1 and goes out. So the final state in this case is applying first U0 and then U1 on the target system. And then you can see if you prepare the other state from the control. So now the photon will have to reflect each time it meets a PBS. And then we see reflects U1, goes around, reflects U0 and goes around. And so the final state you get in this case is first apply U1 and then U0. And then what we want to do, of course, is to start our system in a superposition of the two control states. And so what happens is that the state will just go through in a superposition of the two orders. And because quantum mechanics is linear, the final state will be simply superposition of the two states I've shown before. And so this is exactly the same final state as we had when we consider the gravitational scenarios. And this is a process that is known as the quantum switch. So that's again the quantum control of the causal order between between U0 and U1. So this is yeah, as I mentioned, this is something that can be performed in the lab. There have been quite a lot of experiments. Of course, it's not a full simulation of quantum gravity because of the gravitational scenario, because here the time order is not given by a fundamental delay of the time, but is given by routing the system in the correct way. But still, if you look at what the process is doing in an information theoretic perspective, is doing exactly what it was doing in the gravitational scenario. So from the point of view of information processing, you have all your capabilities. And so as we mentioned, for example, you can get some computational advantage if you have this resource that cannot be represented as a quantum circuit. You can have an advantage in doing certain quantum computation, and there has been a lot of interest in recent years to try to explore more and more protocols where you can have an advantage. So I will very briefly mention other things you can do with the process matrices. So this was a quite broad overview talk. I didn't really touch on any recent result, but things that you can start to study is, for example, how can you communicate in the presence of indefinite causal order? So these can be a little puzzling at the beginning, because in a typical communication scenario, you have a sender and a receiver, and then you have to think of many repetition of a protocol where you have a sender and a receiver whose causal relation is always fixed. You always have first A, and then A prepares the message and B receives the message, and so B has to be always after. And so it can be a little bit confusing to think of this, but if you have this formalism, then it becomes quite natural. And you can calculate things like channel capacity and give bounds on quantum and classical communication capacity. Another thing that is maybe a bit more exotic, you can start to explore closed time-like curves. So these are models for time travel. The standard approaches to closed time-like curves have quite a lot of problems. But one can consider a model based on these process matrices that, in fact, doesn't have all the problematic aspects of other models. Another thing that one can do is that is, if you want to think in terms of these quantum gravity applications, to have some reference frame independence. And what I mean is that in the way I formulated the scenario so far, you still need some reference frame to define your events. So for example, in the gravitational scenario, this was the local clocks. And so these were assumed to be some background classical clocks that you can always tell when is, say, the 2 o'clock for the local background clocks. So that's what allows you to label the events as A, B, and C, and so on. But in general relativity, usually one wants to give a reference frame independent picture when you don't fix any background system. And so that's something that is, again, can be a little unclear how to do at the beginning, but in fact, it turns out you can give a version of this formalism that doesn't need this, this labeling. So these are just a few examples of some relatively recent works on this formalism. So, okay, so it is time to wrap up. So the main message is that it is possible to formulate quantum theory without having a global causal structure in the background. So you don't need to have in the background something like a state that evolves in time, or you don't even have to know in advance what is the order between the events that you want to consider. You can recover all the known quantum theory and even more general scenarios without assuming global causal structure. And indeed, there are situations that are compatible with the local description of quantum theory, and yet cannot be described in terms of any background classical variables that defines their causal order. So that's what we call indefinite causal order. And I've shown with a couple of examples that this is not just an abstract mathematical construct, but it is physically meaningful. And I have presented two physical scenarios. One is when you combine quantum and gravity, and the other is a scenario that you can realize in the laboratory. And importantly, this is a new quantum resource, so it's still under investigation. I will say how much one can really do with this type of resource that you cannot do with, say, ordinary quantum computers. But this is definitely something interesting because it's a new type of resource which can be accessed with the present-day technology. And finally, this is what I mentioned a little more tangentially, but this has a very important application to even to the study of causally ordered scenarios, and that is for non-Markovian open quantum systems. So as I mentioned a few times, if you try to consider general non-Markovian processes, so these are processes where your system interacts with the environment and the environment retains a memory of interaction of the system, then you cannot really describe those processes using time evolution. So also in those cases, you really need to use this description in terms of a quantum causal structure. So in this case, it's causally ordered causal structure, but you still need this type of formalism where you take an all-at-once description and your state over time, your process over time is described by a causally ordered process. And so this is a quite important application, and there are now it's something that is becoming increasingly popular, and it's a very rapidly evolving field study of open systems, of causally ordered processes. And so with this, I would like to thank you, and I can take any question from the audience.
Okay, questions, please. The floor is open for questions. Thanks for completing in time. Questions?
Yeah, may I ask something?
Yeah, sure, please.
Yeah, so the general form of a process matrix, does it always considers Hilbert spaces of states and channels, or can it consider something more? Like,
in the sense beyond quantum theory, or
yeah, so like for example, you showed that you showed one example where the process matrix was composed of the state tensor product with channels, and that can be like separable or in an entangled type of states. But in general, can the terms be something other than states and channels?
Yes. So okay, already. So state and channel, I think you refer to this form where you have an initial state and then a channel that connects the first to the second. Yes, already when you have a non-Markovian process, this is not just the product of a state, and this is because the environment creates correlations between operation at time 1 and operation at time 2 beyond the one given by the channel. So the way you can think of it is that a Markovian process is analog to a product state. So you have a product of initial state and then a channel from A to B. And then the non-Markovian channel is a correlated state, which can also be entangled. So for example, one of the insights here is that you can distinguish between an environment that carries only classical memory to an environment that carries generally quantum memory. And this is exactly the same distinction, or very close to the distinction between a separable state and an entangled state. So if this process is formally analog to an entangled state, then this is the scenario that needs a quantum description of the environment. So you already for these causally ordered scenarios, you have a situation that is not just state and channel. But then if you go beyond causally ordered scenario, indefinite causal order, then you have processes where you cannot really tell what is a state, what is the channel, and yeah, there are different levels of generality, and at some level we don't even have a physical interpretation, and so you cannot really pull apart what you define as a state and which part you interpret as a state and which part you interpret as a channel.
Okay, so you cannot decompose it further.
Yeah, so already in this case, you already cannot decompose it further in the sense if you have an entanglement, that the scenario where you cannot put it as a product of initial and final state, and then you have other scenarios where there is no even decomposition using an external environment. There is no interpretation in terms of states and channels.
Yeah, but you can still say that it lives on the space of A input, A output, and B input.
Yes,
but...
so the state space is always the same. So the state space is always the tensor product space of Alice space and Bob space. But you can have the general processes which, let's say, if you have already here, for example, you see that you will not have a simple situation where one of the two outputs is identity. And so the most general process is something that leaves has non-trivial terms in each input and output case.
Okay.
Yes. This is an example, for example, this is an example where you really cannot say what is the state. So you can, for example, take some partial trace and then define the state for Alice and the state for Bob, but these are really marginals. You cannot build the whole process by putting together those marginals.
Yeah, and will they be positive, the marginals? I mean, do they retain the property of states? Or
yes. So, for example, for this, and this is a completely general property. If you so one has to be a bit careful how to define reduced states, but if you do the partial trace on Bob's side, or more generally, if you plug in a deterministic operation for Bob, then you will have that the reduced process will be a state for Alice and on Alice input and identity on Alice output. And this is a completely general situation. If you have a multi-party scenario and you start to fix deterministic operation in a set of parties, then the reduced process will be a valid process. And if you fix everything except one, then the reduced process will be just a state.
okay. Also, one thing, so you mentioned that is this process matrix a resource that you mentioned at the end? Or
yeah,
you
so the process matrix itself is a mathematical construction, I will say, but there are physical situations that can be interpreted as it can be can be interpreted as resources. Yes.
Okay, like indefinite causal order, you can say it's a resource.
Yes. Yeah, we can say that. I mean, one has to be a little careful what exactly it means resource, but technically you can say that accessing if you have some information process that goes through some indefinite causal order, you can do some things better, or that or more things than you could do using, say, a quantum circuit.
So do they show advantage only in communication, or they can show advantage in other tasks as well? Yes.
Okay, yes. So there have been a lot of works showing advantages or claiming advantages on all kinds of things, from computation to communication to thermodynamics to all sorts of things. Now, to be fair, one has to be a little careful, because when you talk about advantage, you have to be sure you are comparing things in a sort of fair way. So when you talk about computation, for example, the type of advantage, there is one query complexity. So it means you're trying to perform some computation, and then you're asking how many accesses to some black box operation do I need to perform my computation. So in that case, you can make a quantitative comparison between putting your black boxes in a circuit or using them in an indefinite causal order. When you have things like thermodynamics, you can also define, try to define this fairly, but I will say it's a little less developed. So there are some claims that you can have advantages in many situations, but they're not. The comparison is not always made very rigorously, I will say.
Okay. Thank you.
So, any more questions?
Can you hear me? Hello?
Hello?
Yep.
Okay.
Hello? Yeah?
Yeah. So I'm not sure if this is a dumb question, but can we think of these matrices as like some kind of entanglement across time, like?
Yes, in some case. So there are different ways to think about entanglement across time. Thinking about entanglement across time was one of the motivations to start this type of process. So I would say there are two main ways you can think about the entanglement across time. One way is if you just have an ordinary channel. So this is the sort of the simplest situation where you have a system, an operation at time A, and then another operation at time B later, and think that you have something like a unitary operation. then formally the unitary channel from A to B formally looks like an entangled state between the output of A and the input of B. So this is something that has been noticed already in many different forms. One way you can think of it is that if you make some state preparation at A, or if you make some measurement at A and some measurement at B, you can get a perfect correlation. It can violate things like Bell inequalities. So people consider things like Bell inequalities over time. They are closely related to things called the Leggett-Clark inequalities. And so there is a common way in thinking. So you can define just the ordinary evolution as an entanglement between an output space and an input space. And then another way is to think. So in the sense, entanglement is defined based on a subsystem division. So there are different ways you can decompose a process into subsystem. Another way to decompose is to think of a whole subsystem that defines event A and the whole subsystem that defines event B. You can also think about these non-Markovian scenarios where you have a quantum memory as defining entanglement across times, but in a different division of subsystem. So in this case, the entanglement will be between system AI and system AOBI. So you make a tensor product in a different way. So you put AI is one of your subsystem and AO times BI is your other subsystem. And then in this case, entanglement across time represents quantum non-Markovianity. So yeah, there are many ways, and you can make different construction of this type. So there are many ways that you can define entanglement across time depending how you divide your temporal subsystems.
Okay, thank you.
Any other questions?
Yes, ma'am.
Yes, there's one question. Yes, I see a raised hand.
Yes, ma'am. Am I audible?
Yes.
So in the picture of the changing causal structures because of the presence of yes. Am I audible?
Yes.
Oh yeah.
Yes, can you please repeat your question?
Yeah, in the picture of the changing causal structures because of the presence of a mass, if we assume that we have two subsystems A and B already entangled, and then and then the Earth is, and what the mass is actually another entanglement. So if A and B is already entangled, then wouldn't the monogamy of entanglement be violated if we have another Earth entangling with this system?
So A and B are not don't have a prior entanglement. So a more general comment is that monogamy of entanglement will work a little differently in this process that it does with states, although you can still derive some monogamy relations. So in this particular scenario, we are not assuming that A and B are have any prior entanglement between them. So we are just thinking that, yep.
But if in any kind of field theory, we'll have some UV divergences. We will have some UV divergences in the entanglement, right? So it cannot be separable. But there will be some correlation function always there.
So maybe the helpful thing is this one. So if you think about a state, then you will have a correlation between or entanglement between your control system, which is the mass, and then a state which represents the connection between A and B. So for example, if you trace out, in this case, if you ignore the mass, if you trace it out, then you will not see any correlation between any entanglement between in the process in itself. So you will have a mixture of A before B and B before A. So that's why I insist that when people talk about superposition of causal order, that's not really correct, because you really need this control system to see that you have a non-classical or an indefinite causal order. So in this case, your observation about monogamy is relevant because, yes, it is true that if you want to, so again, it's a little subtle to talk about entanglement because you have to define exactly what you're saying. But it is true that the fact that you're entangling R with these process subsystems means that when you trace out R, then you don't have quantum correlations in the causal order itself. So in this case, yeah, there is no tension because it's exactly how it works. That the way to detect this indefinite causal order is to perform operations at A, B, and C. So when you make your final measurement at C, you can effectively project into a superposition between A and B or B or A. But if you don't make a final measurement at C, so this final measurement at C is a final measurement of your control system, of the mass. You need to measure the mass at the end of your experiment to prove that your process had an indefinite causal order. If you don't do that measurement, then everything is just completely equivalent to having a random mixture of A before B or B before A.
So the entanglement between A and B is always dependent on the causal order. We cannot just independently say that A and B are entangled.
So again, you have to define entanglement across what subsystems. So for example, if you have entanglement between AI and BI, that is what we usually call entanglement. So that will be an entangled state across the two input systems. If you have entanglement between AO and BI, this means that there is some coherent evolution from the output of one to the input of one. And again, you can, yeah, there will be some monogamy relation, but yeah, if you want to say there is entanglement between A and B, then it will depend on them. So it's not that you cannot have entanglement if you don't have this control. You can have a scenario where you just have, you just prepare an entangled state within A and B without any mass or any other indefinite causal order. It's just in this case, the entanglement will be just some multipartite property of A, B, and C.
Okay. Okay, thank you, sir. And sir, one more question. Excuse me.
Yes.
Yeah. So one last question here on here we have considered the indefinite causal orders where we have A and I'm not talking about this. I'm not talking about this subsystem. In general, A and B are causally linked to time, and we can take A before B or B before A. But what if we have a scenario in general relativity where that cannot happen? Like for example, if B is in a black hole and A is outside, then in this kind of formalism, how will we represent any kind of entanglement between them?
Yeah, so there have been some works in that direction. I haven't looked in details in that, but yes, in principle, you can do things of that type. So in general, if you have a B inside a black hole, typically that will be in the future of A, in the sense, well, okay, depends what scenarios, but so say that, so you have to think that these are really analogs of events in space and time and not systems that live in space and time. So for example, you can have a word line of an object that falls from outside the black hole to inside the black hole. And then if you define two events along this word line, that will be just two causally ordered events that are not different from any other causally ordered event. Now the scenario that is that would be typical to a black hole is if you start to set around a description of multiple events, and then you can describe particularly the causal structure of a black hole, and then you can try to play around. I can put the black hole in a superposition, and so I can put my events in a superposition of being inside and outside of the black hole and things of that type. So all these things are formally possible. I know there are a few studies around there, not too familiar with them, but it's certainly some fun scenario to look at.
But there will be some back reaction from the black hole as well, right? Because if A and B are not similar systems.
What do you mean back reaction?
I mean, like if we have a highly massive body which is causally connected to I mean, it loses mass while going in the black hole, A to B. So A and if suppose some scenario happens like some Penrose process where it loses mass while going in the black hole. So A is massive, B is not, and then if we just interchange the orders, it will have some kind of difference to the structure of the black hole, the controls black hole. So.
Yeah. So I haven't studied that in detail, but yeah, in principle, you can have a scenario. You can include that situations like a black hole evaporation or yeah, Hawking. The Penrose process will be a bit easier, I suppose, because they're just extracting energy. But But yeah, in this situation, again, you will have to think. So, okay, if the question is that the control system can be involved in the operations as well, and the answer is yes. But again, you have to think, you have to understand how to define your events on the control system. So now you can think that your C will be part of this bigger blob, and maybe A, B, and C are only in the blob, and it's not that C is just after. So you can have a situation where the control, you have operations of the control, and the order between these operations is also possibly indefinite, and it can also affect the order of the other operations. So yeah, in general, you can have all the scenarios. It can obviously become quite complicated.
Okay, thank you, sir.
I think there was one last question.
Well,
I don't think there's a further question. Is there any other
hello?
question?
There was
Sangeet, yes.
Oh yeah, no,
Yeah.
I was just making an observation. Like when you mentioned like the entanglement between the masses, the mass and the process matrix. I guess it's kind of like a genuine entanglement kind of thing, right? Like a GHZ state. Like if you measure the if you make a measurement on the mass, then the other state just loses the entanglement as well. Like
yes, if you make a measurement and you trace out the result, then you lose the entanglement in the other subsystems.
Yeah. So yeah, it just kind of reminded me of the GHZ state. I just want to make that remark. That's all.
Yeah, it's similar. Like the specific form is not that of a GHZ state, but in that sense, it's similar that if you measure one subsystem, then you lose the entanglement between the others.
Okay. Yeah.
So, yes, if there are no further questions, I guess I can thank all the audience and a very interesting discussion.
Can I ask a question? So,
I guess so.
yeah. So thank you for your talk. My question is, did you perform channel capacity estimation while considering causal structure?
Yes.
For example, whether channel becomes super additive, sub-additive, or additive.
So we have some work about channel capacity, but I don't have any result in terms of additivity that is different from the known results in quantum communication. So in fact, the results we have are more like in the negative sense, in the sense that if you consider things like channel capacity, then in fact it's not known if indefinite causal structure can give any advantage to definite causal structure. And if you think about simple scenario where you have just considered the capacity from A to B, then you can prove the Olevo bound. So you can prove that the Olevo bound holds even for arbitrary causal structure. What is unknown if you start to calculate combination of capacity, like say you try to calculate the capacity of A to B plus the capacity from B to A, or if you calculate the average capacity or thing of that type, then it's actually not known if there is any advantage. So it's known that there are advantages for other type of communication tasks, but not really in communication capacity defined in an asymptotic setting. And in particular, as concerns the superadditivity, subadditivity, and all kinds of things, essentially you can prove that if you just consider a communication from A to B, then it's not different from using just a causally ordered quantum channel from A to B. So in this case, the indefinite causal order, in fact, just takes noise, but doesn't make any structural difference. But then, yeah, it's an open question. If you have more complicated scenarios and you want to calculate some combined or joint capacity, then that's all open.
Thank you.
Okay, I think that's all. We should break for lunch now. I thank the speaker. Thank you, Dr. Costa.
Thank you. Enjoy your lunch.
Yes. Okay, so we will end this session. Thanks again.
Thank you.
Bye.
Bye.
Thank you thank you all for the participating in this session. This half of our session ends here. Our next session will start from 3 p.m. and we have quite a good talk in this session. So we are expecting the all participant to present in this session in large number. So okay, thank you.